The universe has no center you could point to, no quiet middle where everything else revolves around it. And yet, everywhere you look, something is circling something else. Planets trace steady paths around stars. Stars drift around galactic cores. Galaxies themselves move in slow, patient arcs, pulled by structures far larger than any single point. If this quiet journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like, a soft tap on subscribe, or simply your presence helps keep these calm explorations alive, and I hold that with sincere thanks. Now, let's begin with the first truth. Part 1. If the universe has no center, why does motion look so organized? If the universe truly has no center, then why does motion seem so orderly, so patterned, so repetitive? At first glance, the night sky feels structured, almost architectural, as if everything knows exactly where to go. But this sense of order doesn't come from a central anchor. It emerges from local relationships, from gravity shaping motion one quiet interaction at a time. What looks like cosmic choreography is really countless small rules playing out together, patiently, everywhere at once. To understand this, it helps to let go of a deeply human habit. We like centers. We build cities around them. We organize stories around a beginning and an end. When we look at motion, we instinctively search for a middle point, something solid and fixed that everything else must revolve around. But the universe does not share this preference. In physics, order does not require a throne, it requires consistency. Every organized motion you see in the cosmos begins locally. A planet does not orbit the universe, it orbits its star. A moon does not orbit existence itself, it responds to the gravity of its planet. Each system is small, self-contained, and governed by the same simple laws repeated endlessly. Gravity pulls, motion carries forward, balance emerges. If you could slow the universe down enough to watch carefully, you would notice that nothing is following a grand cosmic blueprint. There is no master diagram etched into space. Instead, each object responds only to what it can feel. Gravity has no awareness of the whole. It reaches outward blindly, tugging on nearby mass, shaping paths one interaction at a time. This is why motion appears so organized without needing a center. The rules are universal, but the relationships are local. Wherever matter gathers, gravity creates structure. Wherever something moves sideways while falling inward, an orbit is born. And once an orbit forms, it tends to persist, repeating itself with quiet loyalty across millions or billions of years. Think about what an orbit really is. It is not a path chosen with intention. It is the natural result of motion refusing to stop. An object moving forward encounters gravity pulling it inward. Instead of falling straight down, it curves. Instead of escaping, it returns. The path closes on itself, not because it was designed to, but because the balance allows no other outcome. This balance does not care where it happens. It works the same way near a star, inside a galaxy, or around a black hole. The universe does not need a center because the laws that create order do not depend on position. They depend on relationship. Who is near whom? Who pulls on whom? Who is moving relative to whom? From your place on Earth, this can feel counterintuitive. When you look up, you see layers of motion stacked neatly together. The moon circles Earth. Earth circles the sun drifts around the Milky Way. The Milky Way moves within a vast cosmic web of galaxies. It feels as though all of this must be arranged around something deeper, something hidden at the core. But each layer is independent. The moon does not care where the galaxy is. Its motion is defined almost entirely by Earth's gravity. Earth's orbit around the sun is only faintly aware of the Milky Way at all. These motions coexist without coordinating, like overlapping melodies that never need to merge into a single song. This is one of the most calming truths in physics. Order does not require oversight. It does not need intention. It arises naturally when simple rules are applied everywhere, without exception. Gravity does the same thing in every corner of the universe, and so similar patterns appear again and again. You can see this repetition clearly in galaxies. Spiral galaxies, like the Milky Way, rotate in vast flattened disks. elliptical galaxies drift in slower, more chaotic swarms of stars. These shapes were not planned. They emerged from how gas collapsed long ago, carrying ancient angular momentum forward through time. Once that motion existed, it could not simply disappear. Angular momentum is one of the quiet guardians of cosmic order. It is the reason spinning objects keep spinning. It is why collapsing clouds of gas flatten into disks instead of falling straight inward. It is why planets tend to orbit in the same plane and in the same direction. Once motion begins, physics protects it. Even chaos, when viewed closely, follows rules. What appears random at first often reveals deeper structure when observed patiently. The early universe was not smooth and uniform. It contained tiny variations in density, almost imperceptible differences in energy. Over time, gravity amplified those differences, pulling matter together, shaping filaments, clusters, and voids. The result is the large-scale structure of the universe, a vast cosmic web stretching across billions of light years. Galaxies are not scattered randomly. They trace threads of dark matter, gathering where gravity has guided them for eons. There is no center to this web. And yet, its structure is unmistakable. This teaches us something subtle about organization itself. Order is not the opposite of randomness. It is the outcome of repeated interaction. When the same rule applies everywhere, patterns emerge naturally. Snowflakes form intricate shapes, not because they are designed, but because water molecules follow consistent laws as they freeze. The universe works the same way, just on a scale so large it can feel overwhelming. As you rest here, breathing slowly, consider that the sense of calm you feel may come from recognizing this reliability. The universe is not chaotic in the way we often fear. It is predictable, patient, and deeply consistent. Even when it surprises us, it does so within boundaries set by unchanging laws. This consistency is why astronomers can predict planetary motion centuries into the future. It is why eclipses return on schedule. It is why spacecraft can be guided across billions of kilometers to meet distant worlds. The absence of a center does not make the universe unstable. It makes it fair. The same rules apply everywhere, without privilege or exception. From a deeper perspective, the idea of a center may not even make sense. In an expanding universe, every point can be considered central from its own frame of reference. From where you are right now, distant galaxies are moving away in all directions. From their perspective, the same is true of you. Each observer lives at the center of their observable universe, not because they are special, but because space itself expands evenly. So when motion looks organized, it is not because everything is aiming for the same destination. It is because everything is responding to the same principles. Gravity curves paths, motion persists, energy balances itself. Over time, repetition becomes rhythm, and rhythm becomes structure. And perhaps the most comforting part of this realization is that you are included in it. Your body moves with Earth. Earth moves with the sun moves with the galaxy. You are not separate from this order. You are carried within it, held by the same invisible rules that guide the stars. As we continue this quiet journey, another question begins to form. If motion doesn't need a center to be organized, then what does it really mean for the universe itself to have no center at all? Part 2. What does it actually mean for the universe to have no center? When scientists say the universe has no center, they're not speaking poetically. They mean that space itself expands evenly in all directions, carrying galaxies with it like dots on the surface of an inflating balloon. No dot is special. No location is privileged. From anywhere you stand, everything else appears to move away. And yet, within that centerless expansion, local motion still finds patterns of orbit and return. This idea can feel unsettling at first because it challenges how we usually understand space. On Earth, almost everything we experience has a center. A room has walls. A city has a downtown. Even storms spin around an eye. Our instincts tell us that motion must be organized around something solid and fixed. But the universe does not behave like a room or a storm. It behaves more like a fabric being gently stretched. To understand what no center really means, imagine standing anywhere in the universe. From your position, distant galaxies appear to be moving away in every direction. The farther away they are, the faster they seem to recede. This observation is not unique to you. If you were standing on a galaxy billions of light years away, you would see the same pattern. Everything else would still appear to be moving away from you. This is the key insight. The expansion of the universe does not originate from a single point in space. It happens everywhere at once. Space itself is growing, and galaxies are carried along with it. They are not flying through space away from a central explosion. They are remaining mostly where they are, while the space between them stretches. The balloon analogy helps, but only if we are careful. Imagine a balloon with dots drawn on its surface. As the balloon inflates, every dot moves away from every other dot. There is no dot at the center of the surface. The center of the balloon exists, but it is not part of the surface itself. In the same way, the universe may have a mathematical origin in time, but it does not have a center in space that exists within the universe. This distinction matters. When we talk about the Big Bang, it's easy to picture an explosion that happened somewhere, sending matter outward into empty space. But that image is misleading. The Big Bang was not an explosion in space. It was an expansion of space. Every region of the universe was once closer together. There was no empty background waiting to be filled. Because of this, asking where the center of the universe is becomes like asking where the center of the surface of the Earth is. You can choose a reference point, but nature does not assign one for you. Every location is equally valid, equally ordinary, equally unprivileged, and yet, despite this lack of a universal center, structure still forms, galaxies still gather, stars still orbit, planets still follow steady paths. This happens because the expansion of space is incredibly gentle on small scales. Gravity easily overcomes it where matter is close together. Inside galaxies, inside solar systems, even inside clusters of galaxies, gravity dominates, holding structures together against the slow stretching of the cosmos. So the universe can be centerless and structured at the same time. Expansion governs the largest scales, shaping the overall geometry of space. Gravity governs smaller scales, sculpting matter into bound systems. These two effects coexist without conflict, each ruling its own domain. If you could watch the universe from far outside, which is something no observer can actually do, you might see space expanding like a slow, steady breath. But from within the universe, that expansion is subtle. You do not feel it. Atoms do not stretch, bodies do not drift apart. The distances inside galaxies remain stable because the forces holding them together are far stronger than the expansion pulling them apart. This is why the phrase "no center" does not mean no order. It means no preferred location. The laws of physics apply equally everywhere. The universe does not revolve around a throne or a focal point. It unfolds uniformly, governed by rules that do not care where you are. There is something deeply humbling in this realization. Humans have long placed themselves at the center of their stories. Ancient cosmologies imagined Earth as the still point around which everything else moved. Even after we learned that Earth orbits the Sun and the Sun orbits the galaxy, it was tempting to believe there might still be some ultimate center beyond all of it. Modern cosmology gently removes that last comfort. There is no cosmic middle. There is no edge either. The universe does not curve back toward a hub. It expands in a way that makes every observer feel central, while none truly are. This perspective also changes how we think about motion itself. When galaxies move away from one another due to expansion, they are not traveling through space in the usual sense. They are being separated by the growth of space between them. Their local motions, such as rotations and orbits, happen on top of this expansion, layered gently without interference. You can think of it as multiple kinds of motion happening at once. On the largest scale, space expands. On smaller scales, gravity binds. On even smaller scales, atoms vibrate, electrons orbit, particles fluctuate. Each layer follows its own rules, yet none contradict the others. This layered motion is why the universe can feel both dynamic and calm. Vast distances increase, galaxies drift apart, And yet, within your own local region, everything feels stable. The ground beneath you does not stretch. The atoms in your body do not notice the expansion at all. When scientists measure the expansion of the universe, they do so by observing light from distant galaxies. That light is stretched as space expands, shifting toward longer wavelengths, a phenomenon known as redshift. This stretching is uniform. It does not point back to a single source. It tells us that space itself has changed during the light's journey. From these observations, we learn that the universe looks roughly the same in every direction. It has no obvious asymmetry, no large-scale rotation around a central axis, no favored location. This uniformity is one of the strongest pieces of evidence that there is no center. And still, the human mind searches for one. We are drawn to the idea of a cosmic anchor, a place where everything begins and ends. But the universe invites us to think differently. It suggests that meaning does not require centrality, order does not require hierarchy, motion does not require a single origin point. Instead, the universe is relational. What matters is how things connect, not where they sit. Gravity links masses, light links moments across time. Motion links past and future states. Everything exists in a web of relationships that do not point inward, but outward, sideways, everywhere at once. As you rest with this idea, notice how it mirrors your own experience. There is no single center to your awareness. Sensations arise, thoughts drift, breaths come and go. Order emerges not from control, but from balance, from systems interacting quietly, moment by moment. The universe, in this way, feels less like a machine built around a core and more like a living pattern unfolding without preference. No part is more important than another. No location is more real than the next. And as we continue this quiet exploration, another question naturally follows. If the universe has no center in space, how do gravity and motion still manage to create such stable, repeating paths, those gentle orbits that feel almost timeless? Part 3. Why gravity creates circles instead of straight lines. Gravity doesn't pull objects straight inward the way intuition suggests. Instead, it bends paths, turning forward motion into graceful curves. A planet falling toward a star never reaches it because its sideways velocity keeps it moving past. The result is an orbit, not because gravity demands a circle, but because motion refuses to stop. Falling, endlessly missing, becomes revolution. At first, this feels almost like a contradiction. If gravity is a pull, why doesn't everything simply collapse inward? Why doesn't the universe rush toward points of mass like rain toward the ground? The answer lies not in gravity alone, but in motion that already exists. Nothing in the universe begins at rest. Every object carries momentum inherited from its past, from the conditions that formed it. Imagine a stone released from your hand. It falls straight down because its sideways motion is nearly zero. Gravity pulls it inward, and nothing carries it forward. But now imagine throwing that stone sideways. It still falls, but it also moves forward. Its path curves. Throw it faster, and the curve stretches farther outward. If you could throw it fast enough, it would fall around the Earth instead of into it. That stone would become a satellite. This is not metaphor. This is exactly how orbits work. An orbit is not a balance between forces pulling equally in different directions. It is a balance between motion and gravity. The object is always falling inward, but its forward motion keeps it perpetually missing the center. This idea was first understood clearly by Isaac Newton in the 17th century, but it took centuries for its deeper implications to fully unfold. Newton showed that the same force pulling an apple to the ground also governs the motion of the moon. The moon is falling toward Earth at every moment. It just keeps missing. Once you understand this, circles begin to feel less mysterious. They are not preferred shapes, they are consequences. When motion and gravity meet under the right conditions, curved paths emerge, naturally. Not only circles, but ellipses, spirals, and arcs, each shaped by speed, distance, and mass. In fact, perfect circles are rare. Most orbits in the universe are slightly stretched, forming ellipses. Planets speed up when they are closer to their star and slow down when they are farther away. This behavior is described by Kepler's laws, which reveal that orbits are dynamic, breathing paths, not rigid tracks carved into space. What matters most is that gravity does not cancel motion. It redirects it. It changes the direction of velocity without removing it. This is why objects curve instead of stopping. This is why motion persists. In modern physics, this idea goes even deeper. According to Einstein's general theory of relativity, gravity is not a force pulling objects through space. It is the curvature of space itself. Massive objects like stars and planets bend the fabric of space-time around them. Smaller objects follow the straightest possible paths through that curved geometry. From this perspective, an orbit is not even a curve in the traditional sense. It is a straight line drawn on a curved surface. Like a line traced on a sphere, it appears curved when viewed from outside, but locally, it is the most natural path available. This realization removes any sense of intention from gravity. Space does not choose circles. Objects do not decide to orbit. They simply follow the geometry laid out by mass and energy. Motion, once present, continues along the shape of space-time. This helps explain why orbits are so stable. As long as the conditions remain roughly the same, the path repeats. A planet returns to where it has been before, not because it remembers, but because the rules guiding it do not change. Gravity pulls the same way. Motion carries forward the same way. The result is rhythm. There is something deeply soothing about this repetition. In a universe that feels vast and unknowable, orbits provide reassurance. They are promises kept over time. Each return is evidence that the laws of physics have not shifted in the night, and these principles apply everywhere. Electrons orbit atomic nuclei in ways that mirror planetary systems, though governed by quantum rules instead of classical ones. Stars orbit galactic centers. Galaxies orbit within clusters. Even light curves as it passes near massive objects, following paths bent by gravity. At every scale, straight lines give way to curves, not because straightness is forbidden, but because space itself is shaped by what it contains. Motion adapts. Paths respond. It's important to notice that gravity alone cannot create an orbit. If an object began perfectly at rest relative to a mass, it would fall straight inward. Orbits require initial sideways motion. That motion is inherited from the past, from collapsing clouds of gas, from ancient collisions, from the earliest movements of matter in the young universe. Nothing starts fresh. Every orbit is a continuation of a story already in progress. The planets did not suddenly decide to circle the sun. They condensed from a rotating disk of gas and dust left over from the sun's formation. That disk already carried angular momentum. The planets simply inherited it. Angular momentum is conserved. This is one of the most powerful and quiet rules in physics. It means that once something is spinning or moving sideways, it tends to keep doing so unless acted upon by an external influence. This is why ice skaters spin faster when pulling in their arms. The motion does not vanish, it concentrates. In the universe, angular momentum prevents collapse. As clouds of matter fall inward under gravity, they spin faster, flattening into disks. Those disks fragment into smaller bodies, each carrying a portion of the original motion. Orbits are the natural outcome of this process. Seen this way, circles are not shapes drawn by gravity. They are shapes left behind by motion that refuses to disappear. There is also a subtle philosophical comfort here. Gravity does not dominate motion, it cooperates with it. Neither one wins. Instead, they negotiate. The result is a compromise that lasts. When you look up at the night sky and see a planet tracing its slow path among the stars, you are witnessing this negotiation in action. Every moment of that motion is a balance between falling and flying, between inward pull and outward persistence. And this balance is remarkably forgiving. Orbits can be disturbed, stretched, tilted, even reshaped by encounters with other objects, yet they often settle back into new stable paths. The universe allows adjustment. It absorbs change without losing order. This is why solar systems can survive for billions of years, why galaxies remain intact across cosmic time, why motion does not devolve into chaos at the slightest disruption. As you rest now, breathing gently, Consider how this mirrors your own sense of balance. You are not pulled into stillness nor thrown into motion. You exist in a curve between effort and rest, between intention and surrender. Stability does not mean immobility. It means sustained motion along a gentle path. Gravity teaches us that falling does not always mean ending. Sometimes falling becomes a way of continuing, of returning, of moving without arriving. And as we continue this quiet journey, another question waits just ahead. If gravity bends motion into orbits so naturally, then why do these paths feel so stable, so long-lasting, as if balance itself were built into the universe? Part 4. Orbits are not about centers, they're about balance. An orbit is not devotion to a central point. It is a balance between two tendencies, the desire to move forward and the pull to fall inward. Remove either one, and the orbit disappears. This balance exists locally between two bodies, regardless of where they sit in the larger universe. No cosmic center is required, only shared motion and mutual gravity. When we picture an orbit, we often imagine a smaller object obediently circling a larger one, as if the larger body were issuing commands from its center. But this image quietly misleads us. In reality, neither object is truly stationary. Both bodies respond to each other, both move, both participate in the balance. Even Earth and the Sun, which feel so unequal in scale, orbit a shared point called the barycenter. This point lies deep within the Sun, but not exactly at its center. Earth pulls on the Sun just as the Sun pulls on Earth. The difference is magnitude, not principle. Gravity is mutual. Motion is shared. This is the first hint that orbits are not hierarchical structures. They are relationships. They arise wherever two masses interact and exchange momentum. Remove one body, and the orbit vanishes. Remove the motion, and the orbit collapses. What remains is not order, but fall. Balance is the quiet hero here. It is not a static balance like an object resting on a table. It is a dynamic one, maintained through continuous motion. At every moment, gravity pulls inward. At every moment, motion carries forward. Neither ever stops. Stability emerges not from stillness, but from persistence. This is why orbits can feel paradoxical. Something is always happening, and yet nothing seems to change. A planet returns to the same place in the sky year after year. A moon rises and sets with comforting regularity. Motion repeats itself so precisely that it becomes invisible. But this repetition is not guaranteed. It must be earned by balance. If a planet moved too slowly, gravity would win, and it would spiral inward. If it moved too fast, motion would win, and it would escape. Only within a narrow range does an orbit endure. This narrow range is not accidental. It is a consequence of how systems form. When stars are born, they emerge from spinning clouds of gas and dust. That spin is inherited by everything that forms around them. Planets condense already moving sideways. Moons form already in motion. Balance is present from the beginning, woven into the system's birth. Because of this, orbits are deeply historical. They remember the conditions of their formation. Each orbit is a fossil of motion from long ago. Change the past and the present path would look different. The universe carries its memory not in records, but in trajectories. This perspective helps explain why a cosmic center is unnecessary. Balance does not require a global reference point. It only requires local interaction. Two objects are enough. Add a third and the balance becomes more complex, but the principle remains the same. Gravity negotiates, motion responds. In systems with many bodies, such as galaxies or star clusters, this balance becomes distributed. No single object controls the others. Instead, countless gravitational influences overlap, averaging into stable patterns over time. Stars orbit the galaxy not because there is a rigid center commanding them, but because the collective mass shapes the space they move through. Even in these complex systems, balance persists. It shifts, it adapts, it slowly evolves, but it rarely vanishes outright. Chaos exists, but it is often contained within boundaries set by gravity and motion working together. There is a quiet lesson here about resilience. Orbits can tolerate disturbance. A passing object can tug on a planet, altering its path slightly. Over time, the system adjusts. New balances are found. The universe does not insist on perfection, it allows for correction. This adaptability is why solar systems can survive close encounters, why galaxies can merge without dissolving entirely, why structure persists in a universe that is always changing. Balance is not fragile, it is flexible. When we say an orbit is not about a center, we are also saying it is not about control. The larger body does not dominate the smaller through command. It influences it through presence. Gravity does not force obedience, it shapes possibility. This reframing matters because it removes the idea of a privileged position. The center of an orbit is not a throne. It is simply the place where forces balance out. In some cases, that place is empty. In others, it lies between objects. Sometimes it moves. Binary stars offer a clear example. Two stars of similar mass orbit each other in wide arcs, both tracing large paths around a shared barycenter that lies between them. Neither is the main star. Neither is secondary. Their dance is mutual, symmetrical, and enduring. From far away, the system looks elegant and calm. Up close, it is a constant negotiation of forces, energies, and motion. Stability is not imposed. It is achieved moment by moment. This understanding also changes how we think about falling. In everyday language, falling implies failure or ending. But in physics, falling is simply responding to gravity. An orbiting object is falling continuously. It just never finishes. Falling in this sense is not the opposite of stability. It is one of its ingredients. Without falling inward, there would be no curve. Without motion outward, there would be no return. Balance lives between these tendencies, not outside them. As you rest here, consider how often balance in your own life works the same way. Stillness alone is not enough. Movement alone is not sustainable. Calm emerges from a rhythm between effort and release, between attention and letting go. The universe does not search for balance, it produces it naturally when conditions allow. Where motion and gravity meet, balance appears. Where they don't, systems dissolve or collapse. Nothing personal is involved, only physics repeating itself faithfully. This is why the absence of a cosmic center does not threaten order. Order was never dependent on a center to begin with. It was dependent on balance, and balance is local. Every orbit you have ever seen, from the moon's steady path to the slow turning of galaxies, is a quiet demonstration of this truth. The universe does not need a focal point to remain coherent. It needs relationships that endure. And these relationships do endure. They last longer than civilizations, longer than species, longer than planets themselves. They are written in equations that do not age, in motions that do not forget. As the universe expands, as galaxies drift apart, these local balances continue uninterrupted. Expansion does not erase them, it passes around them. Gravity holds its ground where it is strongest, preserving islands of structure in a growing sea of space. So when you imagine the universe without a center, try not to picture emptiness or disorder. Picture instead countless balances, quietly maintained everywhere at once. Picture motion that does not need permission. Picture stability born from movement, not imposed from above. And as we continue this gentle exploration, one more question comes into focus. If orbits are built on balance rather than centers, why does it feel as though everything is always orbiting something nearby, never drifting entirely free? Part 5. Why everything you see is orbiting something nearby. Nothing orbits the universe itself. Everything orbits something close enough to matter. The moon orbits Earth. Earth orbits the sun. The sun orbits the Milky Way. Each motion belongs to its own neighborhood. These layers of orbits stack gently, one inside another, creating the illusion that everything is circling some ultimate point, when in truth, each motion is simply responding to what's nearest. This layered structure is one of the quietest truths in cosmology, and also one of the easiest to misunderstand. When you look up at the night sky, it feels natural to assume that all motion must somehow be connected, that there must be a deepest loop beneath all the others. But the universe does not work its way downward toward a final center. It works outward through proximity. Gravity is not a long-distance ruler issuing commands across the cosmos. It is a local influence. Its strength drops rapidly with distance. What matters most is not what is largest, but what is closest. A distant galaxy has enormous mass, but its gravitational pull on you right now is negligible compared to that of Earth beneath your feet. This is why orbits form in layers rather than around a single anchor. The Moon feels Earth's gravity far more strongly than it feels the Sun's, so it orbits Earth. Earth, in turn, feels the Sun's gravity more strongly than it feels the pull of the galaxy as a whole, so it orbits the Sun. The Sun responds to the collective gravity of billions of nearby stars and dark matter within the Milky Way, and so it follows a slow, vast path around the galactic center. Each orbit is nested inside a larger one, but none of them are subordinated to a universal hub. They coexist, each governed by the strongest local influence. This is why the universe can feel organized without being centralized. If you could somehow zoom out smoothly, passing from the Moon's orbit to Earth's, then to the Sun's, then to the galaxies, you might feel as though you were climbing a ladder toward something final. But there is no final rung. At each scale, gravity fades and another structure takes over. Eventually, even galaxies stop orbiting in any meaningful sense and simply drift apart as space itself expands. This layered motion is sometimes described as hierarchical, but that word can be misleading. It suggests control flowing downward when in reality, influence flows outward. Each object responds primarily to what is closest and strongest. There is no cosmic manager coordinating the motion of all things. There's only gravity, quietly obeying its own rules. This explains why you never see planets orbiting galaxies directly or moons orbiting stars without planets involved. Such configurations are possible in theory, but rare in practice because gravity organizes systems naturally during their formation. Matter collapses locally, forming stars. Around those stars, disks form. From those disks, planets emerge. Around those planets, moons gather. Each level inherits motion from the one before it. The result is not a single orbit, but a tapestry of them. Motion layered upon motion, each path meaningful only within its own context. Even within a single system, this principle holds. Take Earth and the Moon. Both are orbiting the Sun together. From the Sun's perspective, the Moon does not trace neat loops around Earth. It follows a gently wavy path, always moving forward with Earth, never turning back. And yet, from Earth's perspective, the Moon orbits faithfully, rising and setting with comforting regularity. Both descriptions are true. Neither requires a cosmic center. They depend entirely on reference frames and local gravity. Motion is relational, not absolute. This is why the idea of orbiting the universe does not make sense physically. An orbit requires something to fall toward. The universe as a whole is not an object within space. It is the space. There is nothing outside it to pull against, nothing to curve around. Instead, everything that moves does so within the universe, responding to nearby matter. Motion is always local before it is global. Influence weakens with distance. Relationships matter more than scale. There is something deeply calming about this realization. It means that no object is overwhelmed by the weight of the entire cosmos. Each system lives within its own gentle gravitational bubble. The Moon does not worry about distant galaxies. Earth does not feel the tug of the cosmic web. Even the Sun's orbit around the Milky Way is shaped primarily by the mass nearby, not by the universe as a whole. This locality also explains why stability is possible. If every object felt the full gravitational pull of everything else equally, motion would be chaotic beyond comprehension. Nothing would settle. But because gravity diminishes with distance, systems can form, persist, and evolve quietly. It also explains why breaking free from an orbit requires energy. To escape Earth's gravity, a spacecraft must reach a certain speed. To escape the Sun, even more. Each layer has its own threshold, its own boundary of influence. Beyond that boundary, another gravitational relationship takes over. This is why space travel is not about leaving gravity behind, but about moving between gravitational neighborhoods. A spacecraft does not escape gravity altogether. It transitions from one dominant influence to another, using motion carefully, borrowing energy from planetary flybys, slipping from one orbit to the next. Even comets follow this logic. Some are bound loosely to the sun, tracing long, stretched orbits that carry them far into the outer solar system before returning. Others pass through only once, nudged by gravity just enough to change their path, then drifting onward, no longer tied to the sun's neighborhood. Yet even these wandering objects are not truly free. They still move within the gravitational fields of stars, galaxies, and clusters. Freedom in the universe is always relative. The illusion that everything is circling some ultimate point arises because we observe only a few layers at once. From Earth, we see the moon's orbit clearly. We are less aware of Earth's motion around the sun because we move with it. The sun's galactic orbit unfolds too slowly to feel. Each layer fades from perception as it grows larger and more gradual. Our senses are tuned to local motion. We feel acceleration, not steady movement. We notice changes, not constancy. This makes nearby orbits vivid and distant ones abstract. The mind fills in the gaps, imagining a single grand loop that ties everything together. But the universe resists that simplification. It offers instead a mosaic of motion, each piece complete in itself. As you lie here, letting your body grow heavy, it may be comforting to realize that you are held by the nearest thing that matters. Earth's gravity keeps you grounded. The sun's gravity keeps Earth warm and stable. The galaxy's gravity keeps the sun on its long, slow path through the stars. Beyond that, the universe simply expands, gently, without tugging. You do not need to belong to the whole cosmos at once. You belong, first, to what is near. This layered belonging is what allows complexity to exist. Life depends on stability at small scales. Planets must keep steady orbits. Temperatures must remain within narrow ranges. Gravity must be predictable. All of this is possible because influence is local, not universal. So when you look at the sky and see everything moving, remember this. Nothing is racing toward a hidden center. Nothing is trapped in a cosmic whirlpool. Each object is simply responding to the nearest whisper of gravity, tracing a path that makes sense right where it is. And as we continue this quiet journey outward and inward at the same time, another question begins to take shape. If motion is always local, shaped by nearby gravity rather than a universal center, what role does that ancient property called angular momentum play in keeping everything moving the way it does? Part 6. The quiet role of angular momentum. Once something starts moving, it resists stopping. This resistance is called angular momentum, and it is one of the universe's most reliable habits. Clouds of gas collapse into stars and begin spinning. That spin is inherited by planets, moons, and rings. Long after the original cause is forgotten, the motion remains, conserved, steady, and calm. Angular momentum is not dramatic. It does not announce itself. It does not pull or push in obvious ways. Instead, it quietly preserves motion, carrying it forward through time with remarkable loyalty. Once introduced, it tends to endure, shaping systems long after the events that created it have faded into deep history. To understand angular momentum, it helps to think not in terms of force, but of memory. Motion, in the universe, has a way of remembering where it came from. When matter begins to rotate, even slightly, that rotation becomes part of its identity. It is not easily erased. It can be redistributed, reshaped, stretched, or compressed, but it is rarely destroyed. This is why spin appears everywhere. From the smallest particles to the largest galaxies, rotation is nearly universal. Electrons carry intrinsic angular momentum. Planets rotate on their axes, stars spin. Galaxies turn slowly in vast spirals of light. Even systems that appear chaotic often reveal hidden rotational structure when studied closely. The origin of this spin often lies in asymmetry. Perfect stillness is fragile. A collapsing cloud of gas in space may begin almost motionless, but tiny irregularities, slight differences in density or motion, introduce a small twist. As gravity pulls the cloud inward, that twist is amplified. The cloud spins faster as it shrinks, conserving angular momentum. This process is deeply intuitive once you see it. As the cloud contracts, the same amount of rotational motion must be carried by less space. The result is faster spin. The universe does not allow motion to disappear simply because scale changes. It adjusts speed instead. This is the same principle that allows an ice skater to spin faster by pulling in their arms. No new energy is added. The existing motion is concentrated. In space, this principle operates endlessly, shaping stars, planets, and disks of matter with gentle inevitability. When a star forms, it does not emerge alone. The rotating cloud around it flattens into a disk, a quiet consequence of angular momentum resisting collapse in one direction. From this disk, planets condense, each inheriting a portion of the original spin. Moons form around planets in the same way, gathering from rotating debris and carrying that motion forward. By the time a stable solar system exists, its angular momentum has been redistributed many times. The star holds most of the mass. The planets carry much of the rotational motion. Moons add smaller contributions. Rings form where material cannot settle cleanly. Each layer reflects a compromise shaped by gravity and motion working together. What is remarkable is how long this motion lasts. The planets of our solar system have been orbiting for billions of years. Their paths have shifted, stretched, and tilted slightly over time, but the fundamental motion remains. Angular momentum has preserved it through stellar flares, impacts, migrations, and slow gravitational interactions. Even when energy is lost, angular momentum often survives. Friction can convert motion into heat, but unless that heat escapes entirely, the system tends to settle into a new configuration that still carries the original spin. This is why collapsing objects flatten instead of falling straight inward. Rotation redirects collapse, creating structure instead of singularity. This quiet persistence explains why the universe looks organized without central control. Angular momentum distributes motion naturally, creating disks, rings, and orbits wherever matter gathers. No planning is required. The laws ensure repetition. It also explains why motion tends to cluster rather than dissipate. Without angular momentum, gravity would pull matter straight inward, creating dense, featureless points. With angular momentum, collapse slows and spreads sideways. Matter finds paths that allow it to keep moving while still falling inward. The result is complexity. There is a subtle balance here. Too little angular momentum, and systems collapse quickly. Too much, and matter cannot gather at all. The universe exists in a narrow middle ground where both structure and motion are possible. This balance is not imposed. It emerges from the statistical behavior of matter under gravity. When we talk about conservation of angular momentum, we are describing one of the deepest symmetries in physics. It reflects the fact that the laws of nature do not change when systems rotate. Because of this symmetry, rotational motion is preserved. It is a built-in feature of reality. This preservation gives the universe a sense of continuity. Motion does not reset, it carries forward. The present is shaped by the past not just through matter and energy, but through momentum. Every orbit today is an echo of motion long ago. Even galaxies, which formed from vast clouds of matter in the early universe, still spin with patterns set billions of years ago. Their rotation curves reveal how angular momentum interacts with visible matter and dark matter alike. Stars closer to the center orbit faster. Those farther out move more slowly, yet remain bound. The entire structure turns as one. And yet, angular momentum does not lock systems into rigid behavior. It allows for flexibility. Orbits can shift, spins can tilt, interactions can exchange momentum between objects. What remains constant is not the shape of motion, but its presence. Why collisions in space often lead to new forms of order rather than destruction alone. When galaxies collide, their stars usually pass by one another without direct impact. Their angular momentum redistributes, creating tidal tails, rings, and new bursts of star formation. Chaos appears briefly, but balance returns in a new form. The universe is patient with motion. It does not rush to erase it. It lets systems explore possibilities, adjusting slowly over time. Angular momentum acts as a stabilizing memory, preventing abrupt endings. As you lie still now, your own body carries angular momentum. The Earth spins beneath you, the air moves with it. The planet's motion is so smooth and constant that it feels like stillness. This is angular momentum at work, preserving rotation so steadily that it disappears from awareness. There is something deeply comforting in this. The universe does not demand constant effort to maintain order. Once motion is established, it tends to persist on its own. Stability is not fragile. It is supported quietly by fundamental laws. This quiet role also explains why the universe does not wind down quickly. While energy can be transformed and dispersed, angular momentum remains, guiding motion long after systems cool and fade. Stars burn out, but their remnants still orbit. Galaxies age, but their rotation continues. Motion outlives brightness. In this way, angular momentum acts like a whisper from the past, still audible in the present. It carries history forward without words, encoded in paths and spins rather than records. As we continue this gentle exploration, one more question begins to surface. If angular momentum preserves motion so faithfully across time, how does it shape the largest structures of all, galaxies themselves, and what happens when countless spins overlap on cosmic scales? Part 7. Why galaxies rotate without a central anchor. Galaxies spin, but not around a single dense core pulling everything inward. Their motion arises from how matter collapsed long ago, carrying ancient angular momentum forward through billions of years. Dark matter shapes these rotations invisibly, guiding stars along paths they never question. The galaxy turns, not because it must, but because it always has. When you first learn that galaxies rotate, it's tempting to imagine them like cosmic pinwheels, spun by a heavy hub at their center, a giant mass in the middle, tugging everything around it in obedient circles. But this picture, while comforting, is incomplete. Galaxies do not rotate because of a central command. They rotate because motion was present from the very beginning and never disappeared. To understand this, you have to return to the early universe, long before galaxies existed. Matter was spread almost evenly, a thin fog of particles drifting through newly formed space. But almost evenly is never perfectly evenly. Tiny differences in density existed, barely noticeable, but enough. Gravity began to amplify those differences, pulling matter together slowly, patiently, over hundreds of millions of years. As matter fell inward, it did not fall straight. Those same tiny irregularities introduced slight sideways motions, nothing dramatic, just enough to matter. As the collapsing regions shrank, angular momentum grew more concentrated. What began as a faint drift became a measurable rotation. By the time the first galaxies formed, spin was already woven into their structure. This is why galaxies rotate without needing a central anchor. Their rotation is not imposed from the inside. It is inherited from their formation. Each star inside a galaxy carries a small piece of that original motion. Together, those countless motions create the slow, majestic turning we observe today. If you could watch a galaxy form in time-lapse, it would not snap into a neat disk all at once. It would twist, stretch, and settle. Streams of gas would fall inward along filaments. Clumps would merge. Motion would redistribute itself, finding paths that allow collapse without losing spin. Over time, a rotating structure would emerge naturally, not because it was designed, but because the physics allowed nothing else. This is where dark matter enters quietly. Dark matter does not emit light. It does not glow or shimmer. And yet, it outweighs ordinary matter by a large margin. Galaxies form within vast halos of dark matter, invisible scaffolds that shape how visible matter moves. Stars orbit not just what they can see, but what they cannot. One of the great discoveries of modern astronomy came from measuring how fast stars orbit at different distances from galactic centers. If all the mass were concentrated in the visible core, stars farther out should move more slowly. But they don't. They keep moving at nearly the same speed, even far from the center. This flat rotation curve tells us that mass is spread out, not concentrated. Dark matter fills the galaxy. extending far beyond the visible disk. Because of this, galaxies do not behave like planets orbiting a star. There is no sharp boundary where gravity suddenly weakens. The pull is distributed. The rotation is collective. Each star responds to the combined gravitational influence of everything around it, visible and invisible alike. From inside a galaxy, this motion feels calm and stable. Stars follow paths that change only over immense timescales. A single orbit around the Milky Way takes the Sun about 230 million years. In all of human history, it has completed only a small fraction of one galactic year. To us, the galaxy feels still. To the universe, it is turning patiently. What's important to notice is that no star is truly central. Even the supermassive black hole at the Milky Way's core, immense as it is, does not control the galaxy's rotation in the way a star controls a planetary system. Its gravity dominates only the innermost region. Beyond that, the galaxy's mass as a whole determines motion. This removes the idea of hierarchy once again. The galaxy is not a wheel with a hub. It is a dance of countless participants, each contributing to the whole. Rotation emerges from cooperation, not command. Galactic rotation also shows us how deeply the past shapes the present. The direction a galaxy spins today reflects tiny asymmetries from its birth. Collisions and mergers can alter that spin, twist it, even reverse parts of it. But something always remains. Motion is never erased completely. It is redistributed. When galaxies collide, which they often do over cosmic time, their stars usually pass by each other without direct impact. The real interaction happens through gravity. Their dark matter halos overlap, their angular momenta combine. New structures form, tidal tails stretching across space, warped disks, bursts of star formation. After the chaos settles, a new rotating system emerges, carrying a blended memory of both parents. This process has happened many times in the universe's history. The Milky Way itself bears the marks of past mergers. Streams of stars arc across the sky, remnants of smaller galaxies long absorbed. Each one brought its own motion. Each one added to the galaxy's overall spin. And still, there is no anchor. No fixed point around which everything else obediently turns. Rotation belongs to the whole, not the center. This has profound implications for how we think about motion in a centerless universe. Even at scales as large as galaxies, order does not require a focal point. It requires conservation laws and time. Given enough time, matter under gravity finds ways to move that preserve motion while allowing structure. There is also something deeply gentle about galactic rotation. Unlike the fast spin of a planet or the tight orbit of a moon, galactic motion unfolds slowly. Changes take millions of years to become noticeable. Stability is the norm. Violence is rare and brief by comparison. As you lie here now, it may be comforting to imagine the galaxy as it truly is. Not a roaring engine, not a spinning top, but a vast, quiet turning. Stars moving along paths so wide and slow that urgency disappears. Motion without haste, change without disruption. Dark matter ensures this calm by smoothing out gravitational forces, preventing stars from flying apart. Angular momentum ensures continuity by preserving motion across time. Together, they create a system that can endure for billions of years without a central anchor. And this pattern repeats across the universe. Galaxies in clusters move around shared centers of mass. Clusters themselves drift along filaments of the cosmic web. At each level, motion emerges from past conditions, not present commands. The universe does not issue instructions, it remembers. When you look up at the Milky Way stretching across the sky, you are seeing the light of stars embedded in this ancient motion. Each photon has traveled through a rotating system shaped by invisible forces and forgotten beginnings. The order you see is real, but it is not imposed. It is inherited. As this part of our journey comes to rest, another quiet question begins to rise. If galaxies can rotate without a central anchor, guided only by shared motion and invisible mass, what does that tell us about the difference between orbiting and falling forever? And where that boundary truly lies? Part 8. The difference between orbiting and falling forever. An orbit is a controlled fall. You are always moving inward, always missing the center. This delicate failure repeats endlessly, creating stability from motion. If you could pause time and watch closely, every orbit is a quiet negotiation between speed and gravity, never resolved, never finished. At first, the word fall feels wrong here. Falling sounds final. It suggests an ending, a collision, a loss of balance. But in physics, falling is simply the response to gravity. There's nothing dramatic about it. There's only acceleration toward mass. What turns that inward pull into something graceful is motion that refuses to point straight down. Imagine an object released in empty space near a planet. With no sideways motion, it falls directly inward, gaining speed until it strikes the surface. That is falling forever, or at least until impact. But give that same object a sideways push, and the story changes. Gravity still pulls inward, but the object also moves forward. Its path curves. It falls, but not straight down. It falls around. That around is everything. The difference between orbiting and falling forever is not a difference in gravity. Gravity is the same in both cases. The difference lies in velocity, specifically sideways velocity. Orbiting happens when forward motion is just enough to keep missing the center at the same rate gravity pulls you inward. Too little sideways speed, and you spiral down. Too much, and you escape entirely. Between those extremes lies a narrow, forgiving range where motion and gravity cooperate. This cooperation does not stop falling, it reshapes it. From this perspective, stability is not the absence of change. It is the presence of continuous adjustment. At every moment, gravity pulls inward. At every moment, motion carries forward. Neither wins, neither loses. The orbit persists because the argument never ends. This is why orbits feel timeless. Nothing about them needs to resolve. There is no destination. There is only continuation. In classical mechanics, this balance is often illustrated with perfect circles and smooth ellipses. But real orbits are more complex. They wobble, they stretch, they precess slowly over time. Small perturbations from other bodies introduce tiny changes. Yet even with these imperfections, the essential pattern remains. Falling, endlessly missing, continues. The universe is remarkably tolerant of imperfection. An orbit does not need to be exact to survive. It needs only to stay within bounds. This tolerance is why solar systems endure despite constant gravitational nudges. It is why moons do not immediately spiral away or crash down. It is why motion can be both dynamic and calm. There is another subtle difference between orbiting and falling forever. Time. Falling straight inward tends to end quickly. Orbits stretch falling out across vast spans of time. What could be a brief descent becomes a long, slow journey with no conclusion. Time itself seems to soften when motion curves. A planet may take years to complete a single orbit. A star may take hundreds of millions of years to circle a galaxy. The fall is there, always present, but so gentle that it feels like rest. This softness is not an illusion. It reflects how energy is distributed. In a direct fall, gravitational potential energy converts rapidly into kinetic energy. Speed increases quickly. In an orbit, energy shifts back and forth between motion and position. Speed changes, but within limits. Energy remains bounded. Nothing runs away. This bounded energy is the signature of an orbit. It is what distinguishes a system that stays together from one that disperses or collapses. When energy is balanced just right, motion becomes repetitive rather than terminal. In Einstein's view of gravity, this distinction takes on a geometric form. Objects in orbit are not being pulled in the traditional sense. They are following the straightest possible paths through curved spacetime. Falling forever would mean plunging deeper into curvature without enough sideways motion to remain on a stable track. Orbiting means staying on a path that curves around rather than inward. From this perspective, orbiting is not resisting gravity. It is yielding to it in a particular way. It is accepting the shape of spacetime and moving through it without deviation. This idea removes struggle from the picture. There is no fight between motion and gravity. There is cooperation. Each does what it always does. The outcome is balance. The same principle applies at every scale. An electron bound to an atom does not crash into the nucleus because quantum rules shape its motion into stable states. Stars do not plunge into galactic centers because their velocities keep them on long arcs. Galaxies do not collapse into clusters because expansion and motion intervene. Everywhere you look, falling is redirected, not eliminated. This redirection also explains why escape is possible. If an object gains enough sideways speed, it no longer falls inward fast enough to remain bound. Its path opens. The curve stretches until it becomes an open arc. Falling gives way to departure. The object still feels gravity, but not strongly enough to turn it back. Escape, like orbit, is a relationship between motion and gravity. Nothing magical happens at the boundary. There is no sudden release. There is only a gradual shift in balance until falling can no longer close the loop. This continuity is another quiet comfort. The universe does not deal in abrupt changes, without cause. Everything transitions smoothly from one state to another, guided by the same rules throughout. As you lie here now, it may help to imagine yourself within this framework. You are not held in place by force. You are moving with Earth, with the solar system, with the galaxy. Gravity shapes your path, but motion carries you forward. You are falling through space in the most stable way possible. This does not mean danger. It means belonging. The same laws that allow planets to orbit allow you to remain where you are, supported by ground, air, and structure. Stability is not stillness. It is sustained motion within limits. There's also a philosophical gentleness in this idea. Many things we fear as endings are, in another frame, continuations. Falling does not always mean loss. Sometimes it means finding a path that curves instead of breaks. The universe seems to prefer these curved paths. Straight lines are rare on large scales. Motion bends under gravity. Light bends near mass. Time bends with speed. Curvature is the rule, not the exception. In curved motion, nothing needs to arrive. Everything simply continues. This may be why orbits feel so peaceful to contemplate. They embody persistence without urgency, change without conclusion. As night deepens and your breathing slows, consider this image. Somewhere above you, the moon is falling toward Earth and missing. Earth is falling toward the sun and missing. The sun is falling through the galaxy and missing. Each fall is real. Each miss is precise. Together, they create a universe that moves without collapsing. And as we continue this quiet journey, one more question drifts into view. If orbiting is simply falling shaped by motion, how does the expansion of the universe fit into this picture? And why doesn't it pull these delicate balances apart? Part 9. Why expansion doesn't tear. Orbits apart. The universe expands, but atoms remain bound. Planets remain loyal to stars, galaxies stay intact. This is because expansion operates on vast scales, far larger than gravity's local grip. Space stretches between galaxy clusters, not within them. Orbits survive because they belong to regions where gravity speaks louder than expansion. At first, this seems like a contradiction. If space itself is expanding, shouldn't everything inside it be pulled apart? Shouldn't atoms slowly loosen, planets drift away from their stars, galaxies unravel into emptiness? It's a natural worry, and one that scientists took seriously when cosmic expansion was first discovered. But the universe turns out to be far more subtle than that. Expansion is not a force in the way gravity is a force. It does not pull objects apart locally. It is not something that reaches into a solar system and tugs on planets. Expansion is a property of space on the largest scales, noticeable only where gravity is weak enough to allow it to act. To see the difference, it helps to imagine scale. On the smallest scales, the forces that bind matter are overwhelming. Electromagnetism holds atoms together with astonishing strength. Chemical bonds tie molecules into stable structures. These forces are so strong that the expansion of space is completely irrelevant to them. Atoms do not notice the universe expanding any more than a mountain notices the slow drift of continents. Move up a level, and gravity becomes the dominant binding force. Planets orbit stars, moons orbit planets, stars orbit within galaxies. In all these cases, gravity is far stronger than the effect of expansion. The distances involved are small enough and the mass is large enough that gravity easily overwhelms any tendency for space to stretch. Expansion becomes important only when you look at truly enormous distances, millions of light years across, where gravity has weakened enough that it can no longer hold structures together. Between galaxy clusters, where matter is sparse and distances are vast, space stretches freely. Galaxies drift apart not because they are being pushed, but because the space between them grows. This distinction is crucial. Expansion does not compete with gravity everywhere. It competes only where gravity is already weak. Where gravity has established a bound system, expansion simply passes by without effect. You can think of it as a quiet background change rather than an active disruption. Inside a galaxy, space is effectively held in place by gravity. The geometry is dominated by mass. Expansion has nowhere to act. Outside these bound regions, space is free to stretch. This is why orbits survive cosmic expansion. An orbit is a local agreement between motion and gravity. As long as that agreement holds, the larger behavior of space does not interfere. The planet does not need to fight expansion. Expansion does not ask it to leave. The math of general relativity supports this picture. Einstein's equations describe how mass and energy shape spacetime. In regions of high mass density, spacetime curvature dominates. In regions of low density, the overall expansion of the universe becomes noticeable. These effects coexist, each ruling its own scale. From your perspective on Earth, expansion is completely invisible. The distance between you and the wall does not increase. The space inside your body does not stretch. Even the distance between Earth and the Sun remains stable. The gravitational bond is simply too strong. This layered behavior can feel counterintuitive because we tend to imagine expansion as something happening everywhere at once, uniformly, without exception. But the universe does not apply its rules so bluntly. It is precise. It respects context. Even galaxies themselves, while remaining intact, are not entirely immune to expansion's influence. Over billions of years, the distances between galaxies within clusters can change. Clusters may stretch slightly. But within individual galaxies, stars remain bound, their orbits secure. There is also an important difference between expansion and motion. When galaxies move apart due to expansion, they are not traveling through space in the usual sense. They are not speeding away from a central point. They are being carried apart by the growth of space itself. Locally, they may be nearly at rest relative to their surroundings. This is why expansion does not produce drag or stress within bound systems. There is no friction between expanding space and matter. Nothing is being pulled through anything else. The geometry simply changes where it is allowed to. In the far future, this distinction becomes even more significant. As the universe continues to expand, galaxy clusters that are not gravitationally bound to one another will drift farther and farther apart. Eventually, distant galaxies will fade beyond the observable horizon, their light stretched and redshifted until it can no longer reach us. And yet, within our local group of galaxies, gravity will continue to dominate. The Milky Way and Andromeda will merge, new stars will form, planets will orbit. Local motion will persist long after the larger universe has thinned and darkened. This contrast highlights something quietly profound. The universe does not treat all scales equally. It allows intimacy where forces are strong and distance where forces are weak. It permits islands of structure within an ocean of expansion. There's a kind of gentleness in this arrangement. Expansion does not rush in to dismantle what gravity has built. It waits patiently at the edges, shaping the grand outline of the cosmos while leaving the details intact. This is why the phrase, "the universe is expanding," should not be heard as a threat. It is a description of behavior at the largest scales, not a promise of dissolution at the smallest. Your atoms are safe. Your planet's orbit is stable. The galaxy's slow rotation will continue. As you lie here now, it may be comforting to know that you are held firmly within one of these bound regions. Earth's gravity anchors you. The Sun's gravity anchors Earth. The galaxy's gravity anchors the Sun. Expansion flows around these bonds, not through them. The universe seems to understand the difference between connection and separation. Where matter gathers, it allows closeness. Where matter thins, it allows space to grow. This understanding also helps explain why the universe can appear both dynamic and stable. Things change on large scales while remaining familiar on small ones. The night sky looks much the same year after year, even though the universe itself is evolving. Expansion gives the cosmos its long-term direction. Gravity gives it structure. Motion gives it continuity. None of these erase the others. They coexist, layered and respectful of scale. There is also a deeper lesson here about boundaries. Stability does not require isolation from change. It requires the right scale. Orbits survive not by resisting expansion, but by existing where expansion does, not dominate. This mirrors many systems beyond physics. Patterns persist when the forces holding them together are stronger than the forces pulling them apart. When balance is local, global change can happen without disruption. As the universe grows larger, colder, and more diffuse, these local balances become increasingly precious. They are the places where complexity survives, where stars shine, where planets form, where life, at least for a time, can exist. And so, expansion does not tear orbits apart, it simply redraws the map beyond them. As we continue this quiet journey, another question gently presents itself. If expansion shapes the largest scales while gravity governs the local ones, how does perspective, where you stand and how you measure, change what motion and stillness even mean in a universe like this? Part 10. Frames of reference and the illusion of centers. From where you stand, Earth feels still. From space, it spins. From another galaxy, it traces a spiral path through cosmic history. Motion depends on perspective. Centers appear because reference frames create them, change the viewpoint, and the center dissolves, replaced by another equally valid stillness. This idea sits quietly at the heart of modern physics, yet it takes time to truly feel it. We experience the world from inside a single frame of reference, anchored to the ground, carried by the planet, unaware of the vast motion beneath us. Your body does not feel Earth's rotation. You do not sense its orbit around the sun. You do not notice the sun's long journey around the Milky Way. All of that motion is real, measurable, and continuous, yet from your perspective, it vanishes into calm. This is not a failure of your senses. It is a feature of how motion works. In physics, there is no absolute state of rest. There is only motion relative to something else. If everything around you shares the same motion, that motion disappears from experience. Stillness is not the absence of movement, it is shared movement. This is why centers feel so convincing. When you are inside a moving system, it is natural to treat your position as fixed and everything else as moving around you. From Earth, the sky appears to rotate once every day. For most of human history, this made perfect sense. The stars seemed to wheel overhead while the ground beneath remained unmoving. The simplest explanation was that Earth was the center. But when astronomers shifted the frame of reference, the picture changed. Viewed from space, Earth spins. Viewed from the sun, Earth follows in orbit. Viewed from the galaxy, the entire solar system traces a slow, elegant spiral through space. None of these views are wrong. They are different descriptions of the same reality, each valid within its own frame. This is why centers are illusions. They arise naturally when you describe motion from one particular viewpoint. The moment you step outside that viewpoint, the center moves or disappears entirely. The same principle applies everywhere. From the moon, Earth appears to hover in one place in the sky, barely moving. From Earth, the moon rises and sets. From the sun, both Earth and moon follow wavy paths, neither truly circling the other in a simple way. Each description depends on where you choose to stand. Physics embraces this relativity. It does not ask which frame is correct. It asks how the laws behave in all frames. The remarkable answer is that the laws of physics are the same everywhere, regardless of perspective. Motion changes, centers shift, but the rules remain. This insight reached its most profound expression with Einstein. In his theories of relativity, there is no preferred frame of reference, no cosmic stage where motion can be judged absolutely. Space and time themselves adjust depending on how you move. Clocks tick differently, lengths contract, simultaneity dissolves, even time, which feels so steady and universal, becomes relative. Two observers moving differently will not agree on how much time has passed. There is no single now shared across the universe, just as there is no single center. This can feel unsettling at first, but there is also a quiet peace in it. The universe does not demand that you find the correct perspective. It allows many. Each observer carries their own stillness with them, defined by their motion. This is why motion feels layered rather than chaotic. You are moving in many ways at once, but you only feel changes between frames. You feel acceleration when a car starts or stops, but not when it cruises smoothly. You feel turbulence on an airplane, but not its steady flight. You feel Earth's gravity, but not its rotation. Acceleration matters. Constant motion fades away. This distinction explains why orbits feel calm from the inside. A planet in orbit is constantly accelerating toward the body it circles, but that acceleration is steady and smooth. There are no sudden changes. From the planet's own frame, the motion feels stable. The path repeats. Stillness emerges from consistency. This is also why there is no need for a universal center. Any point can serve as a center within its own frame. From Earth, Earth is central. From the sun is central. From the galaxy is central. Each frame tells a coherent story. The universe does not privilege one story over another. It allows them all to coexist. There is a subtle lesson here about certainty. Many questions that seem profound dissolve when you realize they depend on perspective. Asking where the center of the universe is assumes there must be one. Asking what everything is orbiting assumes a single frame. When those assumptions are released, the confusion fades. Instead of a center, the universe offers relationships. Instead of absolute motion, it offers relative motion. Instead of a fixed background, it offers space-time shaped by energy and mass. This relational view is deeply woven into modern cosmology. The expansion of the universe looks the same from every galaxy. Each observer sees others moving away. No galaxy sits at the center of expansion because expansion is not happening from a point, it is happening everywhere. Once you accept this, the illusion of centers becomes easier to let go. They are not wrong. They are incomplete. As you lie here now, you are at the center of your own reference frame. That is not arrogance. It is physics. Everything you observe is measured relative to you. That does not make you special in the cosmic sense. It makes you an observer, which is something the universe always accounts for. This perspective can be comforting. You do not need to locate yourself within a grand hierarchy. You do not need to know where the universe's center might be. Your frame is enough. The laws work here, just as they work everywhere else. Even the idea of being small or insignificant changes when seen this way. Scale is relative too. From the perspective of an atom, you are vast. From the perspective of a galaxy, you are fleeting. Neither view defines your meaning. They simply describe relationships. The illusion of centers often arises from a desire for orientation. We want to know where we stand. Physics offers a different answer. You stand wherever you are, and that is sufficient. The universe adjusts around you mathematically, without judgment. This does not make the cosmos cold or indifferent. It makes it consistent, predictable, fair. The same equations apply whether you are near a star or drifting in intergalactic space. As your breathing slows and your thoughts soften, you might notice how this idea mirrors your inner experience. Thoughts arise relative to awareness. Emotions feel central when they appear, then drift when perspective shifts. Nothing holds the center permanently. Each moment brings its own stillness. The universe, in this sense, is deeply familiar. It does not anchor itself to a single point. It flows through perspectives, allowing each to feel complete while it lasts. And as we continue this quiet exploration, one more question gently unfolds. If centers are illusions created by perspective, what does that mean for the idea of orbiting itself? And why does nothing ever truly orbit the universe as a whole? Part 11. Why nothing ever orbits the universe, itself. The universe is not an object within space. It is space. There is nothing outside it to orbit, no external anchor to fall toward. Orbits exist only where gravity defines a relationship between things inside the universe. The universe itself does not participate in that kind of motion. This idea can feel slippery because language itself resists it. We are used to thinking of things as being in something. A planet is in space, a ship is in the ocean, a thought is in the mind. So when we talk about the universe, it feels natural to ask what it is in, or what it might be moving around. But the universe does not fit inside a larger container. It is the container. Asking what it orbits is like asking what the ocean swims in. Orbits require 3 ingredients. There must be 2 objects. There must be gravity or some equivalent force connecting them, and there must be space between them in which motion can curve. The universe itself satisfies none of these conditions. It is not one object among others. It does not sit at a distance from something else. It does not fall toward anything external. This is why the phrase orbiting the universe has no physical meaning. Orbiting is a relationship between parts of the universe, not a property of the universe as a whole. When physicists describe motion, they always describe it relative to something else. A planet orbits a star. A star orbits a galactic mass distribution. A galaxy moves relative to other galaxies. But at the largest scale, there is no external reference point left. The chain of around what simply ends. This is not because the universe is unfinished or incomplete, but because motion itself is defined internally. The universe contains motion. It does not perform motion relative to something beyond itself. This is one of the reasons why cosmology feels so different from everyday physics. In daily life, we can always step outside a system and observe it. We can watch a spinning top from the outside. We can measure a car's speed relative to the road. But there is no outside of the universe from which to watch it move. Every observation we make happens from within. Every measurement is internal. This means that concepts like velocity, direction, and orbit must be handled carefully when applied to the universe as a whole. When astronomers say the universe is expanding, they are not describing it moving through space. They are describing space itself changing. Distances between distant galaxies increase over time, not because galaxies are racing outward into emptiness, but because the geometry between them is evolving. This evolution does not point toward a destination. It does not curve around a center. It simply unfolds everywhere at once. Because of this, the universe does not have an overall trajectory in the way objects do. It does not have a path. It does not loop back on itself. It does not orbit. It changes internally according to its own equations. This internal change can include motion on every smaller scale. Galaxies can move, clusters can merge, matter can collapse and rotate, but the whole does not circle anything. Sometimes people imagine the universe as a kind of cosmic object embedded in a higher dimensional space, perhaps orbiting or oscillating in some unseen realm. While such ideas can be explored mathematically in speculative theories, they are not part of established physical models. And even in those frameworks, what we call orbit usually loses its familiar meaning. In standard cosmology, the universe is self-contained. Its behavior is described by equations that do not refer to anything outside it. There is no external mass to pull on it, no external space for it to move through, no external time ticking beyond its own. This does not make the universe static or lifeless. Quite the opposite. It means all activity happens within. Motion, change, and structure arise from relationships among its contents, not from interaction with something beyond. This helps explain why questions about the universe's motion often lead to confusion. Asking whether the universe is rotating or drifting or orbiting assumes there must be an external frame to compare it to. But without an external reference, such questions lose their footing. What physicists can ask instead is whether there are internal patterns that resemble rotation. Does the distribution of galaxies show a preferred direction? Does the cosmic background radiation reveal large-scale asymmetries? These are internal questions, answerable by observation. So far, the universe appears remarkably uniform. It looks roughly the same in all directions. No large-scale rotation has been definitively observed. No global spin has been confirmed. This uniformity supports the idea that the universe is not orbiting or turning in any meaningful sense, and yet, inside this uniform whole, motion thrives, it flourishes. The absence of an external orbit does not mean the absence of internal dynamics. In fact, it allows them. If the universe itself were orbiting something, its internal motions would be influenced by that external relationship. There would be tides on a cosmic scale, distortions imposed from outside. But what we observe instead is a cosmos governed by its own internal balance. There is something quietly elegant about this. The universe does not lean on anything else. It does not need support. Its structure emerges from within, guided by rules that apply everywhere inside it. This also means that the question of purpose often shifts when we think this way. If the universe is not going anywhere, not orbiting anything, not moving toward an external goal, then its meaning is not defined by destination. It is defined by process. Stars form, they shine, they die, galaxies assemble, they rotate, they merge, planets cool, life arises. All of this happens without reference to an outside stage. The story is complete on its own terms. As you rest now, it may be comforting to realize that nothing is pulling the universe toward collapse or forcing it to circle endlessly around something unseen. The universe is not in danger of falling out of balance because there is nothing for it to fall toward. Instead, balance exists locally. Stability exists in relationships. Orbits happen where they make sense, between things that can feel each other's gravity. Beyond that, space opens and stretches without direction. This helps clarify why the idea of a universal center feels so tempting but ultimately unnecessary. We look for centers because they give us orientation, but the universe offers orientation through connection instead. You are oriented by what is near, by what influences you directly. Earth's gravity defines down, the sun defines seasons, the galaxy defines long-term motion. Beyond that, the universe simply expands, indifferent to direction. There is no cosmic north, no ultimate up or down, no place where everything gathers, just relationships unfolding in a vast, centerless expanse. And yet, this expanse is not empty. It is full of motion, energy, and quiet structure. Orbits trace their paths where gravity allows. Elsewhere, space stretches and time flows. As we prepare to move forward in this gentle journey, one more question begins to form. If nothing can orbit the universe itself, and all motion is defined internally, then how did the first motions begin at all? And why does rotation seem to appear everywhere we look? Part 12. How early motion set, everything turning. In the early universe, matter was not perfectly uniform. Tiny differences, amplified over time, created motion, rotation, and structure. Once spinning began, it could never be undone. The orbits we see today are echoes of those first uneven moments, preserved like fossils of motion. To imagine the early universe, it helps to strip away familiar objects. There were no stars, no planets, no galaxies. There was only a hot, dense sea of energy and particles expanding rapidly, cooling as it grew. At first glance, this newborn universe appears almost featureless, smooth in every direction. But almost is the most important word here. Perfect uniformity is rare in nature. Even in the earliest moments, tiny variations existed. Slight differences in density, minuscule fluctuations in energy. These were not dramatic irregularities, just subtle imbalances, but they mattered deeply. In a universe governed by gravity, even the smallest unevenness can grow. As space expanded and cooled, gravity began to amplify these tiny differences. Regions that were slightly denser pulled in more matter. Regions that were slightly emptier lost matter. Over time, these small variations became the seeds of structure. Without them, the universe would have remained a smooth, expanding fog, forever featureless. But density alone does not explain motion. Rotation requires something more subtle, asymmetry. If matter had collapsed perfectly straight inward everywhere, there would be no spin. Everything would fall directly toward the densest points. The universe would be quieter, simpler, and far less interesting. What prevented that was imperfection. Those early density fluctuations were not arranged neatly. They were uneven, irregular, slightly skewed. As matter flowed inward, it rarely approached from all directions equally. One side might arrive a little faster, another a little later. These tiny differences introduced sideways motion. At first, that sideways motion was incredibly small, barely noticeable. But gravity does something remarkable when collapse and motion combine. As matter falls inward, any sideways drift is amplified. Angular momentum is conserved. The smaller the collapsing region becomes, the faster it spins. This is how the first rotations were born, not through design, not through forceful twisting, but through gentle imbalance amplified by time. Once rotation appeared, it could not be undone easily. The universe has no global brakes. There is no friction in empty space to erase motion completely. Angular momentum, once present, tends to persist. It can be shared, redistributed, stretched across larger systems, but it rarely disappears. This persistence is why the universe remembers its beginnings, not in words or images, but in motion. Every spinning star, every orbiting planet, every rotating galaxy carries a trace of those early asymmetries. When the first clouds of gas collapsed to form stars, they were already spinning. When disks formed around those stars, the spin flattened them into planes. When planets condensed from those disks, they inherited the motion. When moons formed, they carried it further. Each step preserved the original twist, reshaped but recognizable. This inheritance is why rotation appears everywhere. It is not added later, it is passed down. Even the largest structures in the universe reflect this early motion. Galaxies rotate because the matter that formed them was already spinning slightly as it collapsed. Galaxy clusters show coherent motions that trace back to early flows of matter along cosmic filaments. The cosmic web itself reflects the gravitational amplification of tiny early differences. There is a quiet inevitability to this process. Once the universe allowed imbalance, motion followed naturally. Once motion existed, structure became possible. Once structure formed, it carried motion forward. It is tempting to imagine that the universe might one day settle into perfect stillness, that motion might eventually fade away. But angular momentum resists that outcome. Even as energy dissipates, even as stars burn out and galaxies age, rotation remains. Motion continues in quieter forms. This is why the universe never truly resets. It evolves, but it does not forget. The past is not erased, it is transformed. In cosmology, these early fluctuations are not just theoretical ideas. They are observed directly in the cosmic microwave background, the faint afterglow of the Big Bang. This radiation carries tiny temperature differences across the sky, variations of just a few millionths of a degree. Those differences map the unevenness of the early universe. From these patterns, scientists can trace the origin of all large-scale structure. They can see where matter would later gather. They can infer how motion would emerge. The universe's earliest moments are still visible, stretched across the sky. And within those patterns lies the origin of rotation. It is important to notice how gentle this beginning was. There was no grand spin-up mechanism, no cosmic hand turning a crank, just small differences allowed to grow under simple rules. Gravity pulled, motion persisted. Time did the rest. This gentleness echoes throughout the universe. The largest motions often arise from the smallest causes. A tiny imbalance given enough time becomes a galaxy. A slight drift, amplified by collapse, becomes an orbit. There is also a lesson here about inevitability. Given the laws of physics as we understand them, once the universe allowed small fluctuations, rotation was unavoidable. Motion did not need encouragement, it followed naturally. This means that orbits were not accidents, they were consequences. The universe did not choose to spin, it could not help it. As you lie here now breathing slowly, consider how deeply this history runs beneath you. Earth's orbit around the sun is not an isolated phenomenon. It is part of a chain of motion stretching back nearly 14 billion years. The direction Earth spins, the plane in which it orbits, the motion of the solar system through the galaxy, All of it traces back to ancient, subtle imbalances in the early cosmos. You are resting within a story written in motion. This does not make the universe feel rushed or chaotic. On the contrary, it reveals how patient it is. Small causes unfold over immense spans of time. Nothing needs to happen quickly. The universe is content to let structure emerge slowly, one orbit at a time. It also reveals why perfect symmetry is rare. Perfect symmetry would produce a universe with no structure, no motion, no story. It is imperfection that allows existence to unfold. Slight unevenness becomes creativity on a cosmic scale. There is something comforting in this thought. Stability does not require perfection. Order does not require exact balance. It requires just enough difference to allow movement. As the universe expanded, cooled, and evolved, those early motions became embedded deeper and deeper into its structure. By the time stars and planets formed, rotation was already a fundamental feature. Nothing needed to be added. The blueprint was complete. This is why, even now, billions of years later, we still see the same patterns repeating. Disks, orbits, spirals, rings, motion organized into familiar shapes across vast distances. The universe, it seems, learned how to turn very early on and never stopped. And as this part of our journey settles gently into place, another question rises quietly from the same ancient past. If motion began with tiny imperfections and was preserved so faithfully, why does the universe still feel so calm and orderly today, rather than chaotic from all that inherited movement? Part 13. Why stillness is the greatest illusion of all you feel at rest, because everything around you shares your motion. The air, the ground, your body, all move together. Orbits feel calm from the inside. Only when motion changes do we feel it. Stillness is not the absence of movement, but perfect agreement. At this moment, you may feel completely still. Your body rests. Your breathing is slow. The room around you is quiet. And yet, beneath this calm surface, motion is everywhere. Earth is spinning beneath you at hundreds of meters per second. It is circling the sun at tens of thousands of kilometers per hour. The sun itself drifts through the galaxy, and the galaxy moves within the vast cosmic web. None of this motion announces itself. None of it disturbs your rest. This is the great illusion of stillness. Not that motion has stopped, but that it has become shared. In physics, what you feel is not motion itself, but change in motion. Acceleration, a sudden shift, a deviation from the path you were already following. When a car begins to move, you feel pushed back into your seat. When it stops, you feel pulled forward. But when it cruises smoothly, the sensation fades. The motion remains, but your awareness of it dissolves. The same principle applies on every scale. Earth's rotation is steady, its orbit is smooth. The air moves with the planet, your body moves with the air. There is no friction dragging you backward, no resistance pushing you forward. Everything is in agreement. This agreement is what creates calm. It is why you do not feel the planet turn beneath you. It is why oceans do not slosh eastward as Earth spins. It is why clouds drift gently instead of tearing across the sky. The motion is constant, ancient, and shared. Orbits are the purest expression of this agreement. From the inside, an orbit feels like rest. A planet does not experience itself as rushing around a star. A moon does not feel like it is constantly falling. Within the orbit, gravity and motion are balanced so perfectly that nothing feels strained. This is why astronauts aboard the International Space Station feel weightless. They are not beyond gravity. They are falling around Earth continuously. Their spacecraft, their bodies, the air inside, all fall together. There is no surface pushing back, no change in motion to signal the fall. The result feels like stillness. Weightlessness is not the absence of gravity. It is the absence of resistance. This distinction matters deeply. Much of what we associate with force and motion comes from resistance. The ground resists your weight. The chair resists your body. When resistance disappears, so does the sensation of force. In orbit, resistance is gone. Motion becomes gentle, quiet, almost invisible. This invisibility of motion shapes how we perceive the universe. We tend to believe that what we feel most strongly must be what matters most, but physics teaches the opposite. The most powerful motions are often the least noticeable. Earth's orbit determines seasons, climate, and the possibility of life itself. Yet you never feel it. The galaxy's rotation shapes the long-term fate of stars, including the sun. Yet it unfolds so slowly that it feels like permanence. Stillness, then, is not a special state. It is a perspective. From one frame of reference, you are at rest. From another, you are in motion. Neither description is more real than the other. They are different ways of slicing the same reality. This is why the idea of absolute stillness does not exist in modern physics. There is no universal frame where everything can be declared truly at rest. Motion is always relative. Stillness is always local. Even the quietest moments are full of movement. Atoms vibrate, electrons shift, fields fluctuate. On the smallest scales, stillness disappears entirely. Motion becomes fundamental. And yet, this constant activity does not feel chaotic. It feels stable. Because the motions are balanced, patterns repeat, agreements hold. This is one of the universe's great achievements. It allows immense motion without turbulence. Vast energies flow without disruption. Stability emerges not from stopping, but from synchronizing. Consider how a flock of birds moves. Each bird adjusts slightly to its neighbors. No single bird controls the group, yet the flock glides smoothly, turning as one. From within, the motion feels natural. From outside, it looks coordinated. The universe behaves in much the same way. Local agreements create global calm. This also explains why we notice change so acutely when it happens. An earthquake disrupts the ground's agreement with your body. Turbulence disrupts the air's agreement with the plane. Sudden acceleration breaks the shared motion, and your senses awaken. Your inner ear, for example, does not detect speed. It detects acceleration. It notices when motion changes. This is why you can spin steadily and feel fine, but feel dizzy when you stop. The change, not the motion itself, is what your body responds to. This sensory limitation shapes your intuition. It makes stillness feel real and motion feel exceptional. In truth, the opposite is closer to reality. Motion is constant. Stillness is the special case where change disappears. This has profound implications for how we think about the universe. It means that calm is not fragile. It does not require the absence of motion. It requires consistency. The universe is calm not because nothing moves, but because so much moves together. This is why the night sky feels peaceful. Stars appear fixed. Constellations hold their shapes. Even though everything is in motion, the motions are slow and coordinated enough to appear timeless. This appearance is not deception. It is harmony. As you lie here now, notice how your breath rises and falls. That motion feels gentle because it is expected, rhythmic, shared by your body. If it were sudden or irregular, it would demand attention. Calm arises from repetition. The universe operates on repetition at every scale. Orbits repeat, rotations repeat, cycles repeat. These repetitions create predictability, and predictability creates peace. Even cosmic change unfolds within these patterns. Stars are born and die, but galaxies persist. Galaxies merge, but structure remains. Motion transforms, but does not vanish. Stillness, then, is not a place the universe reaches. It is a feeling that emerges when motion becomes familiar. There is something deeply reassuring in this. It means that you do not need to escape motion to find rest. You are already resting within it. The same laws that carry galaxies across billions of light years also allow you to lie still, supported, untroubled. You're not standing outside the universe's motion. You're participating in it perfectly. This perspective can soften many fears. Change does not always mean disruption. Movement does not always mean instability. Often, it means continuity, flow, agreement. The universe has been moving for nearly 14 billion years, and yet it remains remarkably coherent. That coherence is not enforced. It arises naturally from shared motion and unchanging rules. As your thoughts slow and your awareness drifts, you might find comfort in this idea. You are not fighting the universe to be at rest. You are resting because you are aligned with it. The ground beneath you, the air around you, the planet itself, all move together, carrying you gently through space and time. Nothing is being torn away. Nothing is slipping. Stillness is not something you must achieve. It is something you recognize when motion becomes quiet enough to feel like home. And as this quiet understanding settles in, one final question begins to form, softly, without urgency. If stillness is an illusion created by shared motion, what does that mean for the universe's deepest preference? And does it favor relationships over locations at every level of existence? Part 14. The universe prefers relationships over locations. Physics cares less about where you are and more about how you move relative to others. Orbits emerge from relationships, not coordinates. Two bodies are enough to create structure. Add more, and complexity blooms. No master center is required, only interaction. This idea sits quietly beneath nearly every law of physics, yet it reshapes how we understand motion, order, and even meaning. When we ask where something is, we are asking a human question, rooted in maps, landmarks, and fixed points. When physics answers, it speaks instead about how things relate: distance, velocity, acceleration, influence. These are relational ideas, not absolute ones. A planet does not orbit because it occupies a particular location in space. It orbits because it exists in a relationship with a star. Remove the star, and the orbit dissolves. Change the mass of either body, and the path reshapes itself. Location alone explains nothing. Relationship explains everything. This is why orbits can exist anywhere in the universe. There is no special region where motion becomes orderly. There is no preferred coordinate system where gravity works better. Wherever two masses can feel each other, structure can emerge. This relational focus is deeply embedded in how physics describes reality. In Newtonian mechanics, forces act between objects. In Einstein's relativity, mass and energy shape spacetime, and objects respond to that shared geometry. In quantum mechanics, particles are defined by interactions and probabilities rather than fixed positions. Across theories, relationships take precedence. Even the idea of position becomes slippery when examined closely. In relativity, there is no universal grid laid across space. Each observer carries their own coordinate system, defined by their motion. What matters is not where something is in an absolute sense, but how its position changes relative to something else. This is why the search for a cosmic center ultimately fails. A center is a location without relationship. It implies importance without interaction. Physics has no use for such a thing. Instead, the universe builds itself from connections. Gravity connects masses. Electromagnetism connects charges. Nuclear forces connect particles inside atoms. On every scale, structure emerges from interaction, not placement. Two bodies are enough to begin: a star and a planet and a moon. Their relationship creates an orbit, a pattern that repeats, stabilizes, and endures. Add a third body, and the system becomes richer. Paths become more complex, resonances appear, motion begins to synchronize in subtle ways. This complexity is not disorder, it is layered relationship. Each object responds to multiple influences at once, negotiating its motion continuously. The result can be surprisingly stable. Solar systems persist, galaxies hold together, clusters form and evolve. What matters is not where these systems are in the universe, but how their parts interact. A solar system near the edge of a galaxy follows the same rules as one near the center. A galaxy in a cluster behaves according to the same principles as an isolated one. Location does not change the laws, relationships do. This universality is one of the most calming aspects of physics. There are no favored places where the rules shift unexpectedly, no regions where order suddenly fails because the coordinates are wrong. Everywhere you look, the same interactions play out patiently and consistently. It also means that the universe does not require oversight to remain coherent. There is no need for a central organizer. No master reference point. Local interactions are enough. Given time, they generate patterns on their own. This idea can feel counterintuitive, because human systems often rely on central control. Cities have centers, organizations have leaders, stories have main characters. But the universe does not mirror our social structures. It grows from the bottom up, not the top down. In this sense, the cosmos is deeply democratic. Every particle follows the same rules. Every interaction matters only locally. No single location holds authority over the rest. This relational structure also explains why the universe can be both simple and complex at the same time. The underlying laws are simple. The outcomes are rich. Complexity arises not from complicated rules, but from many simple interactions layered together. Consider a galaxy again. No star knows the full shape of the galaxy. No star aims for the center. Each one responds to the gravity it feels locally. Yet together, they form a rotating disk, spiral arms, and long-lived structure. The galaxy emerges from relationship alone. The same is true in planetary systems. Planets influence each other's orbits subtly. Moons create tides. Resonances lock periods together. Over time, these relationships settle into stable configurations. Nothing needs to be planned. Stability emerges naturally. This preference for relationship over location also shapes how we understand time. Time in physics is not a universal ticking clock. It depends on motion, gravity, and perspective. Two observers moving differently will measure time differently. What matters is their relationship, not an external schedule. Even causality, the idea that one thing leads to another, is relational. Events are connected through space-time. Cause and effect depend on how signals travel, how interactions unfold. There is no single timeline governing all things. From this view, the universe feels less like a stage and more like a conversation. Objects speak through forces, motion answers, patterns form from exchange. This can be deeply comforting. It means that nothing is isolated. Everything participates. Even the quietest object is part of a network of influence, however faint. As you lie here now, you are part of countless relationships. Gravity connects you to Earth. Earth connects you to the sun. The sun connects you to the galaxy. Light from distant stars connects you to events long past. You are never just somewhere. You are always with something. This sense of connection does not require closeness. Relationships can span vast distances. Gravity reaches across space. Light carries information across billions of years. Even so, what matters is not the absolute distance, but the interaction itself. The universe, in this way, does not privilege coordinates. It privileges influence. This also helps explain why meaning in the universe often feels relational rather than positional. Being at the center does not confer importance. Being connected does. A lone point in empty space has no structure. 2 points interacting create pattern. Perhaps this is why the universe feels so full despite its vast emptiness. Even where matter is sparse, relationships still exist. Fields stretch across space. Expansion links distant regions. History connects present motion to ancient beginnings. Nothing stands alone. Nothing needs to be central to matter. As this understanding settles gently, another quiet realization follows. If the universe prefers relationships over locations, then belonging is not about where you are placed, but about how you are connected. And as our journey nears its final chapter, one last question remains, waiting softly in the background. If everything is defined by relationships and shared motion, why does a centerless universe still feel intimate, familiar, and close, rather than distant and impersonal? Part 15. Why a centerless universe still feels intimate. Even without a center, the universe remains deeply personal. You are bound to Earth, Earth to the sun to the galaxy to the cosmic web. These connections form a nested sense of belonging. Motion links everything gently, quietly, without demanding a central throne. At first, a centerless universe can sound cold. If there is no middle, no anchor point, no privileged location, it can feel as though everything is drifting, unmoored, indifferent. And yet, when you look more closely, the opposite is true. The absence of a center does not erase connection. It makes connection essential. Instead of belonging to a place, you belong to a chain. You are held by Earth's gravity at this very moment, not metaphorically, but physically. The ground beneath you pushes upward because Earth pulls you inward. That pull is steady, ancient, and reliable. It does not depend on where Earth sits in the universe. It depends only on proximity and mass. You belong to Earth because Earth is near. Earth, in turn, belongs to the Sun. Its orbit is not an act of loyalty, but a consequence of shared motion and gravity. Year after year, Earth traces the same gentle path, warmed by the same star. Seasons unfold, life adapts. This relationship gives time its rhythm. The Sun belongs to the galaxy in the same quiet way. It does not race, it does not wander freely. It follows a slow arc around the Milky Way, taking hundreds of millions of years to complete a single loop. All the while, it carries its planets with it, including Earth, including you. The galaxy belongs to something larger still. It moves with neighboring galaxies, guided by dark matter and gravity along vast filaments of the cosmic web. These structures stretch across hundreds of millions of light years, connecting clusters and superclusters in a pattern that looks almost organic. At no point in this chain does a center need to appear. Belonging does not require a throne. It requires continuity. This is what makes the universe feel intimate rather than distant. You are not asked to relate to the whole cosmos at once. You are connected step by step, layer by layer, through relationships that matter locally. Each connection is strong enough to be meaningful. Together, they form a bridge from the smallest scales to the largest. The universe does not overwhelm you with its vastness. It introduces itself gently through what is nearest first. This is also why scale feels manageable. You do not need to comprehend billions of galaxies to feel at home. You need only feel the ground, the air, the warmth of the sun. These local relationships are where meaning lives. Physics reinforces this intimacy. The same laws that govern the motion of distant galaxies also govern the motion of your body. Gravity does not change its mind based on distance. Time does not flow differently because of importance. The universe does not reserve its deepest rules for special places. You are not an afterthought in a cosmic system built for something else. You are a natural outcome of the same processes that shaped stars and galaxies. The atoms in your body were forged in stellar cores. The motion that carries you through space began long before Earth existed. This continuity creates a quiet sense of familiarity. You are made of the universe, moving with it, shaped by it. Even without a center, nothing about this feels random. Motion, especially, plays a key role in this intimacy. Everything is moving, but not violently, not chaotically. Motion is smooth, layered, and shared. You move with Earth. Earth moves with the Sun moves with the galaxy. Each motion carries the smaller ones along. There is no moment where you are left behind. This is why the universe feels less like an endless void and more like a flowing environment. Motion provides coherence. It keeps systems together. It allows history to persist. Even change unfolds gently. Stars age, orbits shift, galaxies merge. But these changes happen over timescales so vast that they feel more like slow breathing than sudden disruption. The universe does not rush. This slowness contributes to intimacy. When nothing changes too quickly, stability emerges, patterns repeat, expectations form, life becomes possible. There is also something deeply personal about the fact that the universe does not single out any location as special. If there were a center, everything else would be defined by distance from it. Importance would be hierarchical. Meaning would be centralized. Instead, meaning is distributed. Your location is not special because of where it is special because of what happens there. Relationships, processes, experiences, all unfold locally. The universe does not need a center to feel close, it needs participation. From this view, intimacy is not about proximity to a cosmic core. It is about entanglement with the world around you. Light from distant stars reaches your eyes after traveling for years, centuries, even millions of years. When it arrives, it interacts with atoms in your retina, triggering signals in your brain. A connection is made across time and space, quietly, without ceremony. Gravity from the moon raises tides on Earth, subtly shaping coastlines and ecosystems. The sun's energy drives weather, growth, and metabolism. The galaxy's environment influences the long-term stability of the solar system. Each connection matters in its own way. You are not isolated within the universe. You are embedded. This embeddedness is what softens the idea of vastness. Distance exists, but it does not sever relationship. Influence fades with distance, but it never disappears entirely. Everything participates at some level. The universe, in this sense, feels less like an empty expanse and more like a fabric. Threads cross, patterns overlap. No single thread is central, yet the fabric holds together. As you rest now, you might notice how this mirrors your inner experience. You do not feel centered because there is a single point inside you where everything converges. You feel whole because sensations, thoughts, and emotions relate to one another. Balance emerges from interaction, not location. The universe works the same way. It does not ask you to orient yourself toward a distant center. It asks you to notice what you are already connected to. The ground, the sky, the slow turning of the stars. Even in a centerless cosmos, you are not lost. You are situated within a network of relationships that give you context and continuity. This may be the deepest comfort science offers. Not that the universe revolves around you, but that you belong within it naturally, without exception or privilege. You are not watching the universe from the outside. You are part of its motion, its history, its structure. The same laws that shape galaxies allow you to breathe, to rest, to feel calm. And perhaps that is why when you look up at the night sky, you do not feel displaced. You feel curious, grounded, quietly connected. The absence of a center does not create emptiness. It creates equality. Everywhere is allowed to be complete. As this journey draws toward rest, there is no need to resolve everything into a final point. The universe does not close its story that way. It continues gently through relationships that endure. You are carried within those relationships now, supported, included, moving even as you rest. And in that shared motion, without a center, without a destination, the universe feels close enough to hold you as you drift toward sleep. As this quiet journey comes to rest, you can let the questions soften and drift. The universe does not ask you to hold everything at once. It does not require you to find a center or a final answer or a single place where meaning gathers. Instead, it offers something gentler. A universe without a center is not empty. It is connected. Every orbit we explored, every motion we followed, every balance we traced was not pointing inward toward a throne, but outward toward relationship. Gravity shaping paths, motion preserving memory, expansion giving space where it is needed, and restraint where it matters. Nothing commanding from above, everything responding, locally, patiently. You are part of this same pattern. You are not standing still in a silent void. You are moving with Earth, carried by the sun, drifting with the galaxy, woven into a cosmic web that has been forming since the first moments of time. And yet, here you are, calm, resting, safe. This is the quiet miracle we return to again and again. Motion does not disturb peace. Shared motion creates it. The universe is not rushing away from you. It is moving with you so smoothly that it feels like stillness. There is no need to locate yourself in the grand design. No need to measure your distance from a center that does not exist. Belonging was never about position. It was always about connection. So as your breathing slows and your thoughts become lighter, you can let the vastness of the cosmos feel less like distance and more like shelter. The same laws that guide galaxies also hold the ground beneath you steady. The same rhythms that shape orbits allow this moment of rest. Nothing is asking you to move. Nothing is pulling you away. Everything is simply continuing, gently, as it always has. Thank you for sharing this quiet stretch of time with me. If these moments brought you a sense of calm or wonder, I'm deeply grateful you were here. Now, you can let the universe keep turning without you needing to watch it. You are carried, you are connected, and you can rest.